So last week we we discussed, of course, very quickly. I'll review what we discussed last week. We defined functions, then we defined function of several variables. Then we discussed the concept of limit, and then the concept of neighborhood, how the neighborhood looks, and what does it mean. Like, it is not just approaching from the left or approaching from the right. There are many paths in which we can approach the point. So when we talk about limits now, it is not just uh, approaching from the left and approaching from the right. It is approaching along any path. And the limit exists if these two limits are equal. That's what we discussed last time. And then continuity is if limit exists and is equal to the function value, then the function is continuous. So we discussed certain examples of how we chose a variable path, that is y equal to mx, and along y equal to mx, if the limit is independent of m, then limit converges. We have a definite limit value. Otherwise, we don't have a unique limit value. So limit is not defined if the limit comes in terms of m. So these are some of the topics that we have discussed. And then we began with derivatives. We talked about, defining partial derivatives. Derivative of a function with respect to x. Then we treat y variables as constant and differentiate with respect to x. And derivative of a function with respect to y, we treat x as constant and differentiate with respect to y. And then these are the second partial derivatives. So this where we ended. So now we will continue from here. So some examples of derivatives, very simple. All right. So, okay. If z is equal to f of x comma y is equal to x cube plus y cube minus 3axy, find fx, fy, fxx, fyy, fxy, and fyx. So this is the given function. Now fx is derivative with respect to x. So we can write either dou z by dou x or dou f by dou x, one and the same thing. So treating y as constant, differentiating with respect to x. So this will be 3x square plus 0 minus 3ay y is treated as constant and derivative of x is 1. Fy or dou z by dou y, or we can write as dou f by dou y, will again we differentiate with respect to y, treating x as constant. So we get 0, 3 x cube derivative is 0, y cube will be 3y square minus 3ax. Next, fxx. That means derivative this is d by dx of dou by dou x of dou f by dou x. So differentiating this expression with respect to x. So we get 6x. Similarly, fyy dou square f by dou y square. This is 6y. And then fxy, differentiating. So fxy is dou square f by dou y dou x. It is the f by dou f by dou by dou y of dou f by dou x. First differentiating with respect to x, then differentiating with respect to y. So differentiating this term, this expression with respect to y. So we get derivative of 3x square is 0, and derivative of 3 minus 3ay is minus 3a. Now similarly, derivative of fyx. So fyx is derivative dou square f by dou x dou y. So partial derivative with respect to x of dou f by dou y. So differentiating this expression with respect to x. So again, we get 3a. So here we see that these two are equal. Dou square f by dou y dou x is dou square f by dou x dou y. This is generally the case. Okay. Now let us consider one more example. Just for practice of derivatives. So again, same, z is log to the base e of x square plus y square. Okay. So find second derivative with respect to x, then f x y f y x f y y. So solution. So z is log of x square plus y square. So dou z by dou x in this case will be 1 upon x square plus y square times 2x So 2x upon x square plus y square. Next, dou z by dou y will be similarly 2y upon x square plus y square. Now, dou square z by dou x square is dou by dou x of dou z by dou x. So differentiating this expression with respect to x, this has both x terms in the numerator and denominator. So we'll have to apply u upon v rule. So the denominator whole square, denominator times the derivative of the numerator minus the numerator into the derivative of the denominator. So what we get, take 2 common, x square plus y square minus x square. So we get 2 times y square minus x square upon x square plus y square the whole square. And dou square z by dou y dou x. So d by d, dou by dou y, no, dou by dou x, no, correct, dou by dou y of dou z by dou x. So this is, for this expression, differentiating dou z by dou x with respect to y. So treating x as constant, so function, the terms of y are in the denominator alone. So all others are treated as constant. You will get minus of 2x upon x square plus y square, the whole square, times 2y. So we get minus 4xy upon x square plus y square, the whole square. Next, dou square z by dou x dou y. So this is dou by dou x of dou z by dou y. So let's look at dou z by dou y. This is dou z by dou y. Differentiating with respect to x partially. So treating y as constant. Again, we get minus 2y upon x square plus y square whole square times derivative of the denominator. We get 2x. So we get minus 4xy upon x square plus y square whole square. The last, what is asked? So these two are equal. Dou square z by dou y dou x is same as dou square z by dou x dou y. This is dou square z by dou y square is differentiating dou z by dou y with respect to y. So differentiating this with respect to y, we get denominator x square plus y square the whole square, x square plus y square into derivative of 2y with respect to y is 2 minus 2y times derivative of denominator x square plus y square with respect to y is again 2y. So taking 2 common, we'll get x square plus y square minus 2y square. So it is twice of x square minus y square upon x square plus y square the whole square. Okay. So these are, partial derivatives. Now we have something called as total derivative. We'll discuss that. So let u be a function of x and y. Uh, so let u is equal to f of x comma y be a function of variables x and y such that x is a function of t and y is also a function of t. Okay. So that is x and y are functions of another independent variable t. Then u of f of x comma y can be expressed in terms of t alone. So then thus, so you get a function of t directly. Thus du upon dt can be obtained du by dt is called as the total derivative of u. This is called as the total derivative of u, and this total derivative can be shown like this. Du by dt is same as partial derivative of u with respect to x into derivative of x with respect to t, and partial derivative of u with respect to y times derivative of y with respect to t. This is very, very important. So this is called as the total derivative. So this is the total derivative. Now, also, we can just show du. Du is dou u by dou x times dx. Suppose we multiply throughout with dt, then we get this. So then dou u upon dou y dy. Now this expression is called as the total differential. That was the total derivative and this is the total differential. So note important observation. So this is very clear, very simple. Du by dt will be the partial derivative of u with respect to x and the derivative of x with respect to t plus partial derivative of u with respect to y and derivative of y with respect to t. Now, suppose I want to find, very important, I want to find du by dx, not dou u by dou x, du by dx. Du by dx. How? We have to use this one, partial derivative, sorry, total differential. Total differential is du is dou u by dou x dx plus dou u by dou y dy. So from here, what we get is dou u by dou x is divide by dx. Sorry, du by dx is divide by dx throughout here. So you get du by dx is dou u by dou x plus dou u by dou y times dy by dx. Okay. Now, similarly, we get du by dy will be dou u by dou x into dx by dy plus dou u by dou y plus dou u by dou y. So now, so based on this formula, we can find partial derivatives like this. So simply based on this, suppose let y be implicitly defined in terms of x. Okay, y is implicitly defined. Y is defined in terms of x. However, we cannot write y as an exclusive function of x. So we are using this result to find an implicitly defined function. It is not function of two variables. It is implicitly defined function. For example, x cube plus y cube plus 3axy is equal to 3, let us say. Now there's a function. Y is a function of x, but it is very difficult to write y in terms of x. And we have to find dy by dx. So, or dx by dy. So one way we know is to differentiate. So we can use this, this result also. Okay. So if u is equal to f of x comma y is equal to some constant c, then what we get, differentiating with respect to x, df by dx equal to 0. So this is nothing but using this result, using result 1. This df by dx is dou f by dou x plus plus dou f by dou y times dy by dx. So from here, we get dy by dx is same as minus of dou f by dou x. I'll write it here. Okay. Dou f by dou x upon dou f by dou y. Okay. So dou f by dou x upon dou f by dou y. This is the result. So dy by dx will be the same as this. Now similarly, we can do df by dy, differentiating this whole expression. So right hand side will be 0. So you get dou f by dou x into dx by dy plus dou f by dou y into dy by dy is 1 is equal to 0. So this gives us dx upon dy is minus dou f by dou y upon dou f by dou x. So these are critical results, very, very important results. And next, total derivatives. Now extension, suppose we have, if u is a function of x, y, and z, and x is a function of t, y is a function of t, and z is a function of t, then again, what will be the total derivative? Du by dt is dou u by dou x times dx by dt plus dou u by dou y times dy by dt plus dou u by dou z times dz by dt. Okay, so this is the extension of it. Now this was about the total derivative. Now function is defined in terms of x and y are in terms of defined in terms of t. Then we could do this. And there's a common phenomena, like if a particle is moving in a two-dimensional plane and x and y, it is moving in two-dimensional plane. So, and it has derivative with respect to x and derivative with respect to y. So t is the time. With time, the particle is moving. So how to find the derivative? So this is, we can use partial derivatives this way. This is used in fluid mechanics types of problem where a particle of a fluid has velocity in x direction and velocity in y direction. It is moving. We want to find what is the actual velocity of the particle in the direction of motion. So there, these kinds of derivatives are used, total derivatives. Next, we have a derivative of composite functions. we know in in a function of single variable, in a function of single variable, um, suppose u is a function of v and v is a function of w and w is a function of x. So basically u is f of g of h of x. So how do we do? Suppose I want to find du by dx. So what do I do? df by dg times dg upon dh times dh by dx. This is what? Chain rule. This is the chain rule of differentiation, isn't it? This is for function of single variable. Now, how to do this for function of several variables? Okay. So this is a composite function. Now, a function of several variables. Now let u equal to f of x comma y be a function of x and y where x and y are themselves functions of two other variables r and s. Okay, such that x is a function of r comma s and y is a function of r comma s. So u is a function of x and y, and x is a function of r and s, y is a function of r and s. Okay, so then u of f of u equal to f of x comma y can be written in terms of r and s. So thus we have these results. So the function itself is in terms of r and s. So I want dou f by dou r or du by dou u by dou r. Okay, which is same as dou u by dou r. Now this is how to do this. This is first differentiate u with respect to x and then differentiate x with respect to r. Again, both will be partial in this case. As compared to the previous one, x was defined in terms of t, y was defined in terms of t. So we had to write dx upon dt. But here x is defined in terms of two other variables and we are differentiating with respect to r. So again, it will be a partial derivative. Second term, dou u by dou y times dou y upon dou r. Similarly, dou f upon dou s, or the dou u by dou s will be dou u by dou x times dou x by dou s, dou u by dou y times dou y by dou s. So this is the result. So this is function of two variables. It's a composite function of two variables. Now next is in derivatives, there is the definition of homogeneous functions and their related results. So important, these are very direct results and they are direct formula substitutions, and very sometimes questions are directly asked. If we know the results, it is easy. So a function f of x comma y comma z comma t comma u is said to be a homogeneous function of degree n if it can be expressed in the form x power n times f of y upon x, z upon x, t upon x, u upon x. That means if we can take x common and make all other variables, fraction of x, then it is said to be a homogeneous function. And if x power n term comes out, homogeneous function of degree n, or if f of some scalar k times x, k times y, k times z, k times t, k times u, so on, is equal to k power n times f of x, comma y, comma z, comma t, comma u. So let us look at some examples of homogeneous functions. So homogeneous functions of several variables. So let's say z is x square plus y square upon x plus y. Now this is a homogeneous function or not, we have to see. So best is replace. So I can write two ways. Method one, I will write z as I will take x square common from the numerator, and I'll write this as 1 by y upon x the whole square by. I take x common, this will be 1 plus y by x. So this is x times 1 plus y upon x the whole square by 1 plus y upon x. So we get x power 1. So z is homogeneous function of degree 1. Z is a homogeneous function of degree 1. Next method is replace. So z is equal to f of kx ky. That means I will replace x with kx, y with ky. So what I get, kx the whole square plus ky the whole square by kx plus ky. So I get k square common, x square plus y square, and k common, x plus y. So I'll get k times of f of x comma y. I have to get the original function and factor k out. Now, so from here, so we get z is a homogeneous function of degree 1. So this is how we do it. Second example, we'll take z is x cube into sine of y upon x plus x y z log of x upon y plus z x z square tan inverse z upon y. So it's a complicated function. So now we can take x cube common and write everything in terms of y by x and z by x, so on. Or another method is consider this one. Uh, this should be f. This cannot be z. This has to be u because z is involved anyway. So this one, replace x by kx, y by ky, z by kz. So we get k cube x cube sine of ky upon kx will be k cancels y upon x, plus we get kx times ky times kz log of kx upon ky, we get log of x by y. Then we get kx into kz square times tan inverse of z upon y. So now we can take k cube common. We have x cube sine of y upon x plus x y z log of x upon y plus x z square tan inverse z upon y. Of course, just observing, we can say it is not necessary that we have to do this calculation. In some cases, it's very difficult, but just observing, we can say this. Like here, this is degree 3 term. This is a dimensionless term. All right, degree 0 term. This is degree 3 term. x, y, z. This is degree 0, degree 3, degree 0. So this is like just multiplying with a constant. That's all. So this is x cube, degree 3, x, y, z, degree 3, x, z square, degree 3. The same we get here, even by replacing uh, x, y, z by kx, ky, kz. So f is an homogeneous function of degree 3. F is a homogeneous function of degree 3. That means every term is of degree 3. So now comes a very important result in this. This is the Euler's theorem of partial differentiation for homogeneous functions. Now for function of two variables, if z equal to f of x comma y is an homogeneous function of x and y of degree n, then x times dou z by dou x plus y times dou z by dou y is equal to n times z. This is the Euler's first theorem. Second theorem says x square times dou square z by dou x square plus 2xy dou square z by dou x dou y plus y square times dou square z by dou y square is equal to n into n minus 1 times z. So these are Euler's theorem. So sometimes question is asked in a objective question. And if left hand side is this x dou z by dou x plus y dou z by dou y, directly we can answer it is n times z. So now the Euler's theorem general formula for this was function of two variables. If there's function of n variables, so for an homogeneous function, for a homogeneous function, z is equal to f of x1, x2, x3 up to xk. So homogeneous function of k independent variables. We have x1 times dou z by dou x1 plus y1 times, sorry, x2 times dou z by dou x2 plus x3 times dou z by dou x3 xk times dou z by dou xk will be n times z. This is Euler's formula for general or for a function of k variables. So with this, we complete the concepts of partial derivatives. We have application of derivatives. So we will have to do certain practice. We will do a few problems now for practice. I have a practice exercise which I'll share with you right after this class, but you can uh, do this. Now, let me give some practice problems. All right. So if u is equal to sine inverse of x minus y, where x is equal to 3t and y is equal to 40 cube, find du by dt. Find the partial derivative. No, not the partial derivative. Find the total derivative. We are now talking about the total derivative. So can anyone do that? Can you solve this? Please solve and tell me what is the answer. We have to do du by dt is do you just a second, there is a problem with the connection. We get dou u by dou x times dx by dt plus dou u by dou y times dy by dt. So this is dou u by dou x partial derivative. So we get 1 by, or directly we can write that also. We'll do both ways. So this 1 by under root of 1 minus x minus y the whole square into x, a partial derivative of x minus y with respect to x is 1, into dx by dt is 3, plus dou u by dou y. We get, oh, this is plus only, right? We get 1 upon under root of 1 minus x minus y the whole square times derivative of x minus y with respect to y is minus 1 times derivative of y with respect to t is 4t cube. So 4 into 3t square. Now let us substitute x and y completely in this. So we have 1 minus, sorry, 1 by 1 minus 3t minus 40 cube whole square times 3 minus 12t square. So we get this as numerator 3 times 1 minus 40 square by under root of 1 minus t square times 3 minus 40 square the whole square. Let us see what we can we simplify this further? This is 3 into 1 minus 40 square upon under root of 1 minus t square uh, 9 minus 3 fourths 12 24 t square 16 t power 4. I'm just trying to see if we can factorize this out. So this is 1 minus 9t square plus 24t power 4 minus 16 t power 6. So this can be written as 1 minus 40 square we can get this as we're not able to factorize it for 1 minus, there's a whole cube. No, we're not able to factorize it further. So we can leave it till here. I thought we can factorize and cancel this. So, or one other method is write x as 3t and y as 40 cube and then differentiate alternative, and then directly you get function of t, and then it is just like a derivative of a function. So u is sine inverse of x minus y, which is sine inverse of 3t minus 40 cube. So du by dt is just, direct derivative 1 by root of 1 minus 3t minus 40 cube whole square times 3 minus 12t square. So that's the same thing. What we get by partial derivatives. So this is 9t square plus 24 t power 4 minus 16 t power 6. Okay. Now, okay, now let us talk about this partial derivatives with respect to, so this problem was on just partial derivative, total derivatives. So one more problem based on total derivative. Let's do this. Now I'll do this one. If u is equal to x log xy, where u is log x times log xy, where x cube plus y cube plus 3xy is equal to 1. Then show that du by dx is equal to 1 plus log of xy minus x times x square plus y by y square plus x. Now, for this, see, this is a explicitly defined function. So let us, u is defined in terms of x and y is defined in terms of x, but implicitly, not explicitly. So first step to do is write the total differential. Total differential of u, total differential of u is dou u by dou x times dx plus dou u by dou y times dy. So derivative of u with respect to x. So this is UV rule we can apply. So we get log of xy into 1 plus x times 1 upon xy times derivative of xy with respect to x is y dx plus partial derivative with respect to y, treating x as constant. We get x upon 1 by xy and derivative of xy with respect to y. So you get x times dy. So this is 1 plus log of xy dx plus x upon y dy. Okay, this is du. This is so this is du. Now we want to find out du by dx. So du by dx will be 1 plus log xy into dx by dx plus x by y dy by dx. Now dy by dx I have to find for this expression. Now given x cube plus y cube plus 3xy is equal to 1. Write this as a function f, f of x comma y is equal to 1. Thus dy by dx will be minus dou f by dou x by upon dou f by dou y. So what do you get? Dou f by dou x differentiating f, this expression here left, this is treated as f of x comma y, differentiating this with respect to x. So we get 3x square plus 3y, and differentiating f with respect to y, we get 3y square plus 3x. So 3 cancels. We have minus of x square plus y by y square plus x. So this we have to substitute here. Therefore, du by dx is, substitute here, 1 plus log of xy plus or minus x upon y times x square plus y by y square plus x. So this one is the required answer. Now there are verbal answers. These are something, sometimes they give questions like this, the verbal questions. Next one I'll do this. So this was a simple practice problem. Now think of this one. Now if x increases at the rate of 2 centimeter per second at the instant when where the instant when x equal to 3 and y equal to 1. Now, at what rate must y be changing in order that the function 2xy minus 3x square y shall neither be increasing nor decreasing. Shall neither be increasing nor decreasing. So what we want to now we have to use this concept of total derivative. This function should neither be increasing nor decreasing. Okay, at this particular instant. That means u is, let's say, 2xy minus 3x square y. What we want is du by dt is equal to 0. Du by dt is equal to 0 at for x equal to 3 and y equal to 1. So now we do not know, it is not given that what is x, how is x changing with respect to t, y, how is y changing with respect to t. So the total derivative, we now have to use this result, dou u by dou x into dx by dt plus dou u by dou y times dy by dt. This is given, this we have to find, dy by dt. So dou u by dou x, differentiating with respect to x, we'll get 2y minus 6xy into dx by dt plus partial derivative with respect to y, 2x minus 3x square dy by dt. This should be equal to 0. So at what? Substituting for x equal to 3 and y equal to 1. So substitute. So this implies 2 into 1 minus 6 into 3 into 1 times dx by dt is 2 centimeter per second plus 2 into 3 minus 3 into 3 square dy by dt. So we get here 6 3 is 18. 18 minus 2 is minus 16. Minus 16 into 2 minus 32. And this is 6 minus 27 minus 21 dy by dt is equal to 0. So we get dy by dt must be minus 32 by 21 centimeter per second. So y for overall this expression to have a constant rate at x equal to 3 and y equal to 1. So dy by dt should be this 32 by 21 centimeter per second. Okay, so there are problems of this type. There are problems of, increase of area. You can practice some problems. I'll give some problems on Euler's theorem now. Okay. So if u is equal to tan inverse of x cube plus y cube by x plus y, then these are the results. X du by dx plus y dou u by dou y is equal to sine 2u. We need to show this, and we need to show that x square dou u by dou x square plus 2xy dou square u by dou x dou y plus y square dou square u by dou y square is equal to sine 4u minus sine 2u. Let's say that we can get this kind of a problem in numerical form. For this, look at this expression here. Now, by itself, this is not a homogeneous function, because tan inverse of x cube plus y cube by x plus y, this is not a homogeneous function. Okay, but if you take tan u and let this be z, tan u is x cube plus y cube upon xy. This is a homogeneous function of degree degree 2. Okay, so now it becomes easy for me. I can use this result. Just see here. Now, instead of I want this, so what I'll do, by Euler's theorem for partial derivative for homogeneous functions, x dou z by dou x plus y dou z by dou y is equal to n times z, 2 times z. Okay, now z is tan u. All right, so dou z by dou x will be dou by dou x of tan u, which will be secant square u into dou u by dou x. Similarly, dou z by dou y will be dou by dou y of tan u, which will be secant square u dou u by dou y. So I have used Euler's theorem to simplify this. Now substitute these two in this. So we get x secant square u dou u by dou x plus y secant square u dou u by dou y is equal to 2 times z. Now z is tan u. So we get x dou u by dou x plus y dou u by dou y is equal to 2 tan u by secant square u. So this is 2 sin u by cos u into secant square u can be written as cos square u. So we get 2 sin u cos u. So from there we get x dou u by dou x plus y dou u by dou y is equal to sin 2u. If we had gone, see, if we didn't use Euler's theorem, this problem would have been very complicated. If we would have directly tried to prove this, dou u by dou x. So this tan inverse derivative is, tan inverse x derivative is 1 by 1 plus x square times derivative of this. So partial derivative with respect to x, partial derivative with respect to y. It would have been a very complicated expression. And then that you have to convert it to and show that it is sin 2u, 2 uh, sin u cos u. It will be very complicated expression. So, but by Euler's theorem, we made it very, very simple. How did we choose Euler's theorem? We have to observe. We need to observe that this pattern, this is Euler's pattern, x dou u by dou x plus y dou u by dou y. What we have seen is, although this function is not homogeneous, this expression is homogeneous inside. This argument of tan inverse, this expression is homogeneous. So we use that and we exploited that. So similarly, let us do this one. The second part. Similarly, we have what we have to show, x square dou square u by dou x square plus 2xy, this whole expression. So now z is tan u, which is x cube plus y cube by x plus y, degree 2 term, degree 2 homogeneous function of degree 2. So therefore, by Euler's second theorem, we get x square dou z by dou x square plus 2xy um, 2xy dou square z by dou x dou y plus y square dou square z by dou y square is equal to n into n minus 1 times z. So from here we can actually show this. Now let us do some simplification. So before we write this, first step. So from Euler's theorem,
So you missed the square in the first one. Dou square.
yeah. So from Euler's theorem, we will prove this. X dou z by dou x Okay, we can just use this theorem. We already have got x x dou u by dou x plus y dou u by dou y was shown to be sine 2u, right? Now what we'll do, differentiate this partially with respect to x and differentiate. So this imply differentiating with respect to x partially. We will get dou by dou x of x dou u by dou x plus dou by dou x of y dou u by dou y dou by dou x of sine 2u. So what we get here is x dou square u by dou x square okay plus um, dou u by dou x times 1 plus this remains constant y dou square u by dou x dou y is equal to, this is cos 2u times 2 dou u by dou x. Okay, let this remain first equation. So this is 2 cos u dou u by dou x. Now similarly, differentiating with respect to y partially. Let this be 1, let this be 2. Differentiate the first equation with respect to y partially. So dou by dou y of x dou u by dou x plus dou by dou y dou u by dou y plus dou by dou y sine 2u. What we get is x dou square u by dou y dou x plus y dou square u by dou y square plus dou u by dou y is equal to 2 cos 2u dou u by dou y. This is 3. Let us do like this now. We already know this expression, x dou u by dou x plus y dou u by dou y. So this is dou u by dou x. You can multiply this with respect to x and multiply second equation with x, third equation with y, and add. So now uh, x multiplied by equation 2 plus y multiplied by equation 3 and adding them up. So when you do this, the x multiplied by equation 2 is x square. X square dou square u by dou x square plus x dou u by dou x plus xy dou square u by dou x dou y is equal to 2 cos 2u x dou u by dou x plus, now we have multiplying the third by y. So xy dou square u by dou y dou x plus y square dou square u by dou y square plus y dou u by dou y. It's 2 cos 2u y dou u by dou x. So we are adding these two. So this will give x square dou square u by dou x square plus these two terms are equal. Dou square u by dou x dou y and dou square u by dou y dou x. These two are equal terms. So this will be 2xy dou square u by dou x dou y plus y square times dou square u by dou y square plus x dou u by dou x plus y dou u by dou y. On the right hand side, we get 2 cos 2u times x dou u by dou x plus y dou u by dou y. Now that has been proven to be equal to sine 2u, this one. So x square dou square u by dou x square plus 2xy dou square u by dou xy plus y square dou square u by dou y square will be equal to, take this to the other side, you get 2 cos 2u sine 2u minus sine 2u. So we get sine 4u minus sine 2u. Okay, so this is the way we solve. So this is an example of how you can apply Euler's theorem to simplify. The last part of today's discussion, a very important, very important part is the concept of Jacobian. And we get a number of questions in GATE on this. This Jacobian. This term Jacobian comes in conversion of um, integrals also, uh, in substitution we convert one differential to another differential. So to use that, we will use this concept of Jacobian. So we will see this in multiple integrals. So the concept of Jacobian, if u and v are both functions of two independent variables, these are functions of two independent variables x and y, then the determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y, that is the determinant. In short, we write as u subscript x, partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, partial derivative of v with respect to y. This is called as the Jacobian. This is the Jacobian of u comma v with respect to x and y, and is denoted as as dou u comma v by dou x comma y, or more commonly, if it is written like this, it is not dou xy, it is dou x comma y. More commonly, it is Jacobian of u comma v by x comma y. So this is the representation, Jacobian of u comma v or x comma y, which is same as dou in brackets u comma v by dou x comma y, is nothing but determinant of ux, uy, vx, vy. This is Jacobian. When we do partial derivatives, when we are doing integration of multiple integrations, one variable or set of two variables being converted to other two variables, this is very, very useful. Now the same Jacobian for three variables. Okay. Now if u comma v comma w are functions of x comma y comma z, then the Jacobian of u comma v comma w with respect to x comma y comma z, or you can write this as uvw upon x y z is equal to the determinant of u, partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of u with respect to z, same partial derivatives of v with respect to x, y, z, partial derivative of w with respect to x, y, z, this determinant. So this is called as the Jacobian. Next, properties of Jacobian. Properties of Jacobian. We have the Jacobian of u comma v with respect to x comma y times the Jacobian of x comma y with respect to u comma v is equal to 1. Okay. So this is j dash is equal to 1. That is the idea. Then suppose there are variables. So just look at this. Jacobian of uv with respect to xy is same as Jacobian of uv with respect to rs multiplied by Jacobian of rs with respect to Jacobian xy. So it is like du by du by dx is du by dr into dr by dx. So that way. So Jacobians are used in that fashion when they are multiple. Two variables are defined in terms of two other variables. So that is when we get this. So these are important results. Now, if This is another one. If u comma v are functions of x and y, then u and v are independent if Jacobian of u comma v and with respect to x comma y is not equal to 0. If this Jacobian is equal to 0, then u and v are independent functions. Similarly, u comma v comma w are independent if Jacobian of uvw with respect to x comma y comma z is not equal to 0. If uvw are functions of x, y, and z. All right. So these are the properties of Jacobian. All right. So this whole chapter is now complete. This whole unit on derivatives is now complete. Derivatives for functions of several variables. So I'm just going through very quickly. Partial derivative we have defined. Then how the definitions of partial derivatives. What are partial derivatives graphically? Last time I explained using graphs. That will be useful when we study, maxima, minima. Then we did a few problems today on partial derivatives. Then this concept of total derivative. This total derivative concept comes when a function is defined in terms of two independent variables x and y, but they are defined, both x and y are defined in terms of t. Then we can have a derivative of this function u with respect to t. This is called as the total derivative, and this is called as the total differential. And from this, we can do du by dx, du by dy, we can find. And we have df by d. If you have an implicit function, then we can always find dy by dx in terms of the partial derivatives and dx by dy in terms of partial derivatives. So total derivatives is useful in this particular manner for implicit functions. Now, derivative of composite functions. We saw how partial derivative u is a function of x and y, and x is a function of RNS and y is a function of RNS. Then derivative of f or derivative of u with respect to r is partial derivative of u with respect to x and multiplied by partial derivative of x with respect to r plus partial derivative of u with respect to y times partial derivative of y with respect to r. So this is how we do it. Same with respect to x. Then we discussed what are homogeneous functions, and for homogeneous functions, there are, Euler's theorems for homogeneous function of degree n. This is the Euler theorem. We didn't go by the proof of this theorem. We just use this theorem. And using this theorem, things become easy many times. We chose one example. Of how a difficult problem by using Euler's theorem can be simplified into an easy problem. And I'll be sharing now some exercises which are very good for practice. See, generally, function of several variables, students do not have enough practice. So when a problem comes, they're not clear about it, how to go about. So I'll give a worksheet, although it appears to be basic, but that practice is very helpful to strengthen the concept. And this concept of Jacobian is same as the derivative concept for function of several variables. So it is Jacobian is defined as the determinant. It's defined as the determinant. So dou u by dou x into dou v by dou y minus dou u by dou y times dou v by dou x. This is the determinant. So we have defined Jacobians, and this is the properties of Jacobians. So I'll end here. I'll give a problem sheet. Tomorrow's class will be a very important class. It will be on maxima and minima of functions of several variables. And this is a very critical point. We get problems on maxima and minima of functions of several variables. Simple problems, but we get them. So we can try to solve. Once we do maxima and minima of functions of several variables, then we are left with one more topic, multiple integrals and their applications.